Hello, science fan. This is going to be part 2 of definitely going over some electron dot diagrams, which we call the Lewis dot diagrams. First of all, let's name this. This is covalent, right? So this is going to be sulfur. And since there are 4 fluorines, we're going to call that tetra for 4. And fluorine turns to fluoride, right? So tetrafluoride. All right, there is a certain note here. It says sulfur is an exception. Remember, that means when everybody else is looking for 8, the octet, and sulfur usually is looking for 8, don't get me wrong, but occasionally it'll hold 10 and be happy. So that doesn't mean it starts with 10 electrons, just in the end it can hold 10. So we'll keep that in mind. But let's break this down. 1 sulfur and 4 fluorines. All right, each fluorine has 7 valence electrons, right? They're all halogens, group 17. And sulfur has 6. So when you add all those up, 7 times 4 is 28, plus 6, you're going to end up with 34. Now, who's going to go in the middle for this? Well, sulfur's the oddball. So let's make sulfur in the middle. And let's surround it with fluorines. Remember to start, I'm going to make everybody happy, give them 8 electrons. So sulfur is definitely going to do a single bond to each fluorine, and when it does, it already has 8. So right now, in our normal rules, that's pretty happy, but we do know there's something about this 10 we'll have to deal with eventually. But let's get everybody happy first. Around the fluorines, we know that they're going to want 8 electrons as well. So each fluorine will get 3 lone pairs of electrons. Remember, lone pairs are just the electrons that are not involved in the bonding. Now, when you count all of that up, there's 8 around each fluorine, so that makes a total of 32. But we want to use 34. Now, normally I'd say well, something's wrong here because everybody's happy with 8. We shouldn't need any more electrons. But for some reason, we know sulfur is an exception where sometimes it can hold an extra 2 electrons. So what do? We're literally just going to stick them right on that sulfur right off to the side. All right? So if we clean this up and did the single bonds for the Lewis dot diagram, there'd be a single bond to each sulfur. Sorry, a single bond to each fluorine. And each fluorine would get 3 lone pairs still. Bop, 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 bop. But then sulfur would have that little extra pair on there to make 34 total. So fluorine's happy with 8, fluorine's happy with 8, fluorine's happy with 8, fluorine's happy with 8, and sulfur actually is happy with 10 in this case. All right? But there you go. You got the Lewis dot structure for sulfur tetrafluoride. All right, this last one on page 1 of our practice is one we know well, right? This is carbon dioxide. But carbon dioxide is going to be our first example when we're going to work on a double bond if the things don't work out naturally. So first of all, each carbon has 4 valence electrons. It's in group 14, and oxygens have 6. That's a total of 16 electrons when I add all of them up. All right, now carbon's the oddball, so we're going to put carbon in the middle, and we're going to put an oxygen on each side. Could you have put the oxygens up top here or here? Absolutely. This just happens to be the way that I drew it. Now we know that everybody's going to need to at least be bonded to something, so I'm going to do a single bond between each carbon and oxygen, and I'm going to give everybody their lone pairs to give them a full 8. And when I do that, oxygen's happy with 8, carbon's happy with 8. And the other oxygen's happy with 8. But here's the deal. When I count them up, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons I used, and I can only use 16. So I'm using way too many, which means I got to start doing some double bonds. So if you remember from practice, double bonds are going to be 2 pairs of electrons between the elements. So I'm just going to start with one of them having a double bond, and because of that, those 4 in between, this oxygen that I just drew on only needs 2 lone pairs, all right? If I have a single bond to carbon, oxygen has 3 lone pairs, and if you look at carbon, it's touching 6, right? It has 4 here and 2 here, so it only needs 2 more to get 8. Now when I count up all those electrons, I now have 4 right here, 6 right here, 8, 10, 12, 14, 16, 18. So good news, I went from 20 to 18, but unfortunately I'm still not hitting that 16 number. So it looks like I'm going to need another double bond. So since we did one on this side, let's try a double bond on this side as well and see if we can get down to that 16, which you see we will. All right, let's do a double bond between this carbon and oxygen and this carbon and oxygen. Now, if you look, 2 double bonds on carbon already means that carbon's touching 8 electrons, so it does not need any lone pairs. So all that's left are 2 lone pairs on each of the oxygens. Now, let's check everything. Is oxygen touching 8 electrons? Yes. Is carbon touching 8 electrons? Yes. Is this oxygen touching 8 electrons? Yes. Let's make sure we count up, though, because everyone's stable. Did we use 16? So 2, 4, 6, 8, 10, 12, 14, 16. Congrats. We've got the right Lewis dot diagram because not only is everyone touching 8, but we're only using 16 electrons. So let's rewrite that really quick. Carbon is double bonded to each oxygen, and each oxygen has 2 lone pairs of electrons. Now we have a good solid Lewis dot diagram. Everybody's stable with 8, and we only use the right number of 16 electrons. All right. Best of luck, science fam. Thanks for following along. Hopefully you're starting to get more comfortable with Lewis dot diagrams.